Hey guys, welcome back to my channel. Hope you are doing extremely well. This is a very own mascot at this side. So first of all, before starting this video, I want to thank you for the previous video overwhelming response. Really guys, I was very much flattered and as well feeling very much loved, right? So keeping up the energy, let's continue today's problem. And it says flatten BST to sorted list. Alright, let us have a look. What does the question says? The question states that you have been given a BST. What is a BST? A binary search tree. The only difference between a binary search tree and a binary tree is that in a binary tree a root's values is something say x, and the values in the left subtrees are, let's say, y, and the right subtree are z. So if it is a binary search tree, then x will always be greater than y and x will always be less than z. Alright? This is the property which makes a binary tree a binary search tree. So for this problem, you can see that 4 is actually greater than 2, 4 is actually greater than 1, 4 is actually greater than 3. And for right subtree, you can see 4 is actually greater than 6, 6 is actually greater than 7, 6 is actually greater than 5. Oh, 6 is actually greater than 5 and 6 is actually less than 7, right? You can check for all nodes that it is following the BST property. So it is a binary search tree. Today's objective is to convert this BST to a list, a type of linked list, but not exactly a linked list. Like the node structure of the answer is similar to BST only. There, we have not been provided with a linked list node specifically. We have to make this BST node as a linked list only. Such what I'm trying to say is a linked list node has two things: the value and the next pointer. If it is a single linked list, right? A BST, or I can say a binary tree node, has a structure of value, left child, and right child. All right. So in the sense we have been asked to present an answer in the form of a linked list, but the linked list node is given in the form of a binary tree node only. I will tell you what does it mean. So a linked list in the form, if you represent this BST in a sorted order, you can see the minimum value here is 1, which is the leftmost point. After that comes 2. So these fours are 1, then are 2, and then 3, right? 3. And then we come to 4. Then we come to 5. Then we come to 6. After that, we end our traversal at 7. Right? These are all the nodes in the sorted order, right? Sorted order. This is the answer we have to give in the return as an output. Now the arrows are representing the right subtree in the case, and the left subtree for all the nodes here will be null. This is a required output, right? Answer of this form is considered to be correct. So I hope you are clear with the feeling of what is the input and what is the output. Input is a simple BST and output is a linked list in the form of a BST only. All right. So we have to present a sorted order where each left is null and the right consists the next node. All right. Now let us move towards the approach. So if you see that when I was drawing the sorted order, I started my traversal from here and then drew along, right? Do some of you know how to take out the traversals? Let us forget the question for a moment and let us see how to figure out the traversals. So the tree given to us is the three types of traversal for a binary tree are pre-order, post-order, in-order, right? I think you agree with me here. Now the simple trick to calculate the pre-order, post-order, in-order if you don't know is, for pre-order, apply some dashes here on the left side, right? And start traversing from here and go till all the nodes are covered. So if you start traversing from here, this one is cutted first, so it will be 4. After that 2 is cutted, so it will be 2. After that 1 is cutted, so it will be 1. After that 3 is cutted, so it will be 3. After that 6 is cutted, So it will be 6 here. Then after that 5. Then after that 7. Right? This will be a pre-order traversal for the given tree. Similarly, for the post order, you have to apply the edges on the right side and do the same traversal from here till here, right? Till here. Okay. Talking about the in order. If we draw the in order traversal for this subtree, let me remove them. For the in order traversal, like here you applied on the left side, here you applied on the right side. For the in order, you apply on the down side, this one. This is a simple trick to calculate the traversal, right? I also learned it from the YouTube community only. So hats off to the YouTube community which provides the content for free. So in order traversal will also start like this, going here, 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 then cut the one, right? Cut the two, right? Cut the three, right? Cut the four, right? Cut the five, right? After that six, then seven, six, seven. So this is my in order traversal. The thing I want you to notice is this is a sorted order and this is not by chance. The BST has a property. The BST, let me change the ink. BST has a property that its in order gives a sorted output. All right. So this is a very important property if you want to clear OS and binary tree question is asked somehow. All right. So this was the concept we are going to use. Now we wanted a sorted order. In order will give us a sorted order, correct? What can we do? We will just traverse the binary tree, traverse the binary tree, and by traversal I mean the in order traversal. Store the node's value, make a linked list with the help of BST nodes only, and return. This is a simple algorithm for today, right? This is a simple algorithm. Okay. So what are the what is the time complexity and space complexity? Let's analyze. So the traversal you will require O of n, correct? For storing you will require O of n space complexity. It is time complexity. It is space complexity. Making a linked list with the help of BST nodes. Again O of n and returning O of 1. So you can see the time complexity is also O of n, the space complexity is also O of n. And if you will see the question given, the goal, the expected time complexity and space complexity are also same. But please read the problem statement carefully. It says here that you must accomplish this without using any extra space except for recursive calls, right? Here we were storing them, so our space complexity is actually using the storage area. This is different from the recursive calls. The questions demand us to use the space only for the recursion calls. I'm not saying that this code will not work. If you will write the code for this algorithm, which I will not tell you how to write, I hope you are all familiar with this type of coding, right? If you will write the code for this algorithm, it will work absolutely like butter knife and your code will run smoothly, your streak will be maintained. But you are here and it's my duty to provide you the best content possible. So I will be providing you the alternative solution which the question is actually asking for, that will be using the recursion stack space only as the extra time complexity. Okay, so the optimized version of the code now. Optimized code. All right, let us draw the tree again. So the tree is 4, left subtree as 2, right as 6, and then 1, 3, 5, 7. One thing we have been marked is we have to go leftmost, then root, then we have to go leftmost, after that root, after that right. So the approach I came up with is, if I keep a pointer, right, like a linked list node head, right, and then update. So if I keep a pointer named as previous right now, right? Previous, right? This will be my something sort of temp in the case of linked list, and I will update my previous accordingly. Now, let me assign previous as -1 first. It will be a new node of -1. Okay. So my previous is consisting of -1. So as said, we have to go left, left, left. So I will also go left, left, left. So I will be standing here at the first. I will be going here at 2. I will explore that 2 also has a left side, left side. Go here, right? Now 1 doesn't have a left side. So when 1 doesn't have a left side, my left side is particularly exhausted, correct? So what I will do is my previous is at -1. Let me draw here, right? Previous is at -1. This is my previous, right? I have to attach 1 to the right subtree because I told you that my answer consists right subtree as my next and left as my null, right? So my previous is at -1. I want to take this node and attach to my right. So what I will do, I will attach it to the right. Done. Attach it to the right. Okay. After that, what I have to do is, I've attached this. Suppose this was my current element, right? So I've attached it to the right. Now, my algorithm says that after left, I have to go to the root. So root is attached. Okay. Now I will explore the right because after root there comes a right. But this node doesn't have a right. It is also null, so nothing can be happen. But after attaching previous here, let me name this node as dummy node because this is a dummy for storing the prev, right? After attaching pre, let us shift here. Let us shift the p here, right? This recursion call will be ended and it will move back to the this node, right? Now, the recursion call for two's left is finished with this node, right? After left, what I have to do? 2. I have to insert the current element. This is my current right now, right? So, attach a 2 here. Attach a 2 here. But two's left consists of 1. Keep in mind, we are attaching this node. We are not making a clone. We are attaching this particular node and two's left is 1. But we want a null. So after attaching, when I move the prev here, I will have to move the prev here, right? Make it null, right? After making it null, go to its right. After you go to its right, you see that this recursion call will go here for 3, right? For 3, no left subtree, no right subtree. After exploring the left, I will have to push it here. So push it here 3. My prev comes here. For 3 also make it null. It is already null, but for safety sake, make it null, right? 3 also null. 3 doesn't have a right side, so nothing else can be happen. Recursion call ends. After exploring this side, recursion call for 2 also ends, and we went back to 4, right? We went back to 4. Okay, my current is here. Left subtree of 4 is exhausted, so push 4 into the linked list. Simple. 4 here, null here, previous here. Go to the right of the 4 now because left done, root done, go to the right. That is a step. So I went to the right. My current is here. But before pushing current, I have to check its left also, right? So 5 is existing in the 6 left. So go here. Current becomes here. As happened here, do exactly same here. So 4 will get attached to 5, null, p will get shifted here, and the recursion call will go back to 6. 6 will be pushed into the linked list. So 5 attached to 6, previous moves here, null here, and then go to 7 because of the right property. Then 7 comes here, previous comes here, null, right? Now my previous is here, right? And I have to make last node also has null, right? So after all the calls, make prefs right equals to null. But at the time of returning, I have dummy in my hand and I have my previous in my hand. I have to return this node. I have to return this node. So what I will do is I will return dummies, right? That is my head of the linked list. That was the simplest algorithm you could ever find on the entire YouTube, and I'm not bragging it. I have tried my best to put in all the effort. If you have still not understood, please comment down. I will be happy to share this with you, share the knowledge with you. Okay. So let us see the pseudocode. Let us see the pseudocode. Before sharing the pseudocode, I would like you to focus that left, root, right. What does it state? Left, root, right is the policy for in order. So we have done nothing but made some acute changes to in order to obtain our answer, right? And this is what happens when you are trying to crack the interviews, when you're trying to crack the OAs. You have to make some acute changes into the existing algorithms to make your answer work. But those acute changes will only occur to you at the time of test if you have practiced enough. Okay. Stay with me, we will be practicing many more questions. So our algorithm would work something like, let us name the algorithm as in order only, right? So we have a previous and we have a current in the in order. I will write the driver function afterwards. So what do we do? If my current is equals to null, that is it doesn't exist. I cannot do anything in that case, right? So return doesn't do simply anything. Otherwise, if it is not null, then what were we doing? We were first exploring the left subtree. So go for in order of previous with curves left. After you have done the curves left, that is left subtree, push the root into the subtree and then push the root into the linked list and then explore the right. So what we are doing is to push the current into the linked list, press right will become cut, right? And after that, pref will become equals to cut, right? And after that, to change the value of left to null, pref's left will become null, right? And then at last, explore the right also. Explore previous with right. Curse right actually, right? This is the code. The driver function, we did two steps in driver function. Let us name it as main only. So what are the two steps? We created a dummy node is equals to new node. Assign whatever value you like, -1, -2, -3, any value from any range. Okay. Then my previous will be assigned to dummy. After that, my what do we say? In order will be called in order with prev, and my say I was passed as root. So root, and after that return dummies right. This is my whole algorithm, and I don't think that this requires a dry run again because the algorithm I showed you here was the best dry run for the algorithm, right? Best dry run for the code. So let us just code it down. In the meantime, please subscribe to my channel. I cannot stress this more. Please subscribe to my channel. I'm only bringing into content because you have been showing a great response, guys. A great response. Really, thank you. I cannot thank you enough, and I don't think that I would have gotten a much lovelier audience than you have. Okay, so what were the steps? Create a node, name it as dummy, new node. Let us give the value of -1. Our previous node will be dummy only. After that, in order, send the previous with the root, right? And after that, return dummies, right? This was the code for the main function, which is a flatten BST in this case. Just have to code the in order. So void in order node star previous node node star root, right? So what are we doing here? The thing we are doing here is, if my root, let us name it as cur because you will be familiar with the cur because we were using cur in the case of dry run also. So if cur equals to null, in that case return simple. Otherwise, explore the left subtree. So in order of prev with curse left. After that, prev's right will become cur. Then prev will become cur. Then prev's left will become null. After that, in order of prev with curse right. And after that, return. This is the simplest code, right? Now this is your task to analyze whether it is using any extra space other than the recursive stack space. Okay, so let us compile and run it. So it is running fine for compile and run. Let's try it for submit also and then end the video with a positive vibe. In the meantime, please subscribe, guys. Bus, I can just say that. So you can see we have completed our 63-day streak, and that was all for today. We'll meet tomorrow with the same energy and solve the another POTD. Hope you liked the video. Subscribe to my channel, and then if you like the video, do drop in the comment and like the button. Okay. So meet you tomorrow. Have a nice day. Yeah.